Welcome to the next lesson of the full-time GoDev program in the concurrency chapter, by the way. And today in this lesson, this episode, we are going to discuss, or I'm going to teach you some stuff about mutexes and atomic values. It's very important because, like I mentioned before, concurrency in Golang is a very important aspect. It's basically why the language is built. It's the bread and butter. It's basically the Hercules of concurrency, the Hercules of distributed programming, in my opinion, and I think a lot of others share the same. But with distributed programming, with concurrency, comes complexity, right? It's a different style of programming, and it's hard to debug, and you can come into a lot of problems. And why do we come into a lot of problems? Well, that is because we have the concept of state, right? The concept of state. And what are we doing with a state? Well, we gonna basically set a state, or I will do it like this. We're gonna set a state, or we are going to update states. We probably also going to delete state, actually, right? We're also going to delete state. So basically, we have state, and we're going to manipulate that. And I'm going to give you an example, like usual, and show you some stuff, right? So basically, let's say we're going to have state here, and that state is going to be a structure. And in state, we're going to have a count, right? And this count is going to be an integer, just to keep things simple. But it doesn't matter. It could be a string. It could be a struct or something else. It actually doesn't matter. Some variable inside of something, or even just a plain var, right? It could be even var count int, right? It doesn't really matter. Something, right? Some variable. And we could do something like this, right? Let's say we're gonna make a for loop, y equals 0, y is smaller than, for example, 10, and then we're gonna say y plus plus, right? And then we're gonna say, first of all, let's make a state. Let's initialize a state here. So we're gonna say state is going to be state. Does not need to be a pointer. It doesn't really matter. Could be, could not be. And we're gonna say that the count is basically, I don't know, maybe 1 or something, right? Nobody cares about the count. And we are gonna do, actually, to be honest, let's do nothing, right? Because what Golang will do, and I'm pretty sure I'm covered this in the very first videos, that if you don't specify your field in your struct, right, what's going to happen is that Go will basically automatically initialize your fields to the default value of that type. And in case of an int, it's going to be 0. In case of a string, it's going to be an empty string. In case of a float, it's going to be 0 float, and all that stuff, right? So it's fine. So the count is going to be 0. Perfectly fine. So what we're going to do here in this function, we're going to make it very simple. We're going to say state count, for example, equals y, right? And let's print out the state here, to be honest. Why not? Println state. And then we're going to say go run main.go, boom, and we have 9, right? So what we're going to do, basically, I'm going to move this code into a test so we can do some cool stuff with it. And I think I have a main test here from, yes, it's basically from back in our beginnings. So we're going to delete this, and I'm going to basically copy everything over. I'm going to copy over the state. Actually, to be honest, state can be here. We're going to say, can you guys see this? Yes. We're going to make a test. We're going to say test state, right? It's going to be a T, testing. You already know how to test in Golang. Testing.t, right? Just like that. And I'm going to copy everything from inside of this main function into this test. I'm going to delete this. And now we are in our test here. So what I'm going to do is I'm going to say go test. I think I could do it like this, minus v minus run test state. To be honest, we could just go test because we have only one test. You can, like I mentioned, you could basically test one single test if you specify the dash run. But in case we only have one test, it doesn't really matter. You're going to say go test. The whole shebang here, minus v, right? You see, and we have 9, right? The state is 9. And let's print this a little bit more verbose. So we're going to say percentage plus v, new line, state, just like that. And then we're going to do it again, boom. And we're going to see that the count is 9, perfectly fine, no problem. So when are the problems showing up? When do we have bad news? Well, that is if we basically make a go routine of the state. Instead of updating the state like normally, we are going to say, yo, go func. This is the syntax for an anonymous go function, right? And we're going to spin up a go func. And inside of that go func, right? So we're going to loop 10 times. And each loop, you're going to spin up that go function. And that function is going to update the state. It's going to set the count, right? And actually, to be honest, what we're going to do is we're going to say count plus 1. This is actually even more bad news because this will give us inconsistent results. So loop variable I captured by func literal. Well, this is very important because you're basically using I inside of a function that basically does not really have the scope of Y, right? Because in a function, you have also a scope. And in a for loop, you have a scope, and then this function has a scope. So what we need to do basically to fix that, it's very important to say y int, and then pass in y, just like that, right? We need to do that because it's basically just a function, and we need to capture that y. Okay, so if we run this, right, let's run this test real quick. What's going on here? Yes, no, that's not true. What am I doing here? Let's type it out, doesn't matter, -v. If you do this, the count is going to be 0, and that's because we, like I mentioned before, each time we're going to spin up a go routine, it's going to schedule that and doing it in a non-blocking way. So it basically means that, well, our program already exited. Our program already quit before we can actually do some stuff and actually print out the real state, the real value of state, right? So in order to basically fix that, we could do some stuff with channels, right? Actually, to be honest, let's do that with channels, right? Because we are in the concurrency course, so why not? So we could do something like the result channel. Here is going to be make me a chain of, actually, to be honest, guys, something I never actually showed you, weight groups. I'm going to show you it right now. Weight groups, if you, let's do that. So we're going to make a weight group. It's going to be a sync.weight group. Man, didn't I show this to you before, right? So we're going to say sync.weight group. And we're going to say each time we're going to spin up this go func, right? Actually, to be honest, each time we are here, each loop, we are going to say vg add, right? We're going to add 1 to the weight group, right? So it's going to be a counter instead of the weight group. It's going to be 9 loops actually. So it's 10, I guess. So it's going to be 10. We're going to add 10 times. And it basically, if we say here, vg.wait, what's going to happen here is that this weight group is going to wait until these 10 increments are basically also 10 times decremented. So when are we done? Well, we are done if we set the state. So we're going to say vg done, right? That makes a lot of sense, right? Because this function will basically be scheduled somewhere else. And so we're going to add, for each loop, we're going to add 1 to the weight group. And for each function that has done its job, right? It's basically doing work, right? Doing some work here, right? And when it's done, we're going to basically say done working, right? So it's basically 10 times incrementing, 10 times decrementing, and it's going to wait until it's back to 0, if that makes sense. And when everybody is done, then we're going to print out the state, and then we should probably see something, but it could be that it's 0. We never know, but it probably won't. Boom. And the state is 9. That's perfectly fine, right? So, and you could see, let's do it again. Boom, state 9. But that's basically cached, right? So we're going to say go test -v minus count equals 1. And this basically makes sure that we don't cache it. It's a little trick that I'm always using, right? So let's run it a couple times, and it stays. You see, now the count is 1, right? Count is 1 because we don't know the order of execution of these go funcs, right? Because we spinning them up at the speed of our CPU, and they're going to do some stuff, and who's going to be first? Nobody knows, right? But still, we don't see anything problematic in our code, right? There's nothing problematic, there's no errors, everything seems to work fine, and that is exactly the problem of programming in a concurrent approach, because everything seems to be normal, but it isn't. And why? Let me show you. We're going to say here, we're going to do this --race. And that basically means you're telling the Go tester, the Go toolkit, that you're going to test this function and that it needs to check for race conditions. Because, and I'm going to explain to you what a race condition is, but first let me show you the error. There is a data race condition, right? And we're going to see, very important, and if you're going to debug these race conditions, is that you're going to check what's the previous write and then also the previous read, right? Where is that thing? Right here. We don't actually read directly. I said, no, we don't actually read it, but it doesn't matter. It doesn't matter at all. Sometimes you could see where it's writing and where it's reading, but in our case, we actually don't read the state because we only write to the state. That's fine for now, right? I'm already thinking ahead. That's what I'm a little bit choking. So basically, what is a race condition? A race condition is basically where multiple Go routines, multiple people are basically trying to write to the same variable. So we basically loop 10 times and we spin up 10 Go routines, and all these Go routines are basically going to set the state, the count of the state, at the same time, or at least almost at the same time or at the same time. And that can give problems, right? Because if you expect value 4, but the guy that is going to provide you another value that you need for your calculation, but this guy is not the first one, there is another guy before that guy, and you get a different value, all your calculations are going to be bad, right? They're going to be invalid because you have a wrong value, right? That will never happen if you run in a normal program, but if you use concurrency, that's a big problem. So how are we going to do that? We need to find a way to synchronize, right? We need to find a way. You need to basically think about this like there is one cake, one big pie, and there is a flag, the yellow flag, right? And there are 10 people in line, and there is a pie. But only if everybody basically just goes at the pie to eat, what's going to happen is that most of the time, the last one is basically not going to have any piece of the pie anymore because everybody just eat the pie, right? That's a problem, right? And who is going to eat it first? Nobody knows, right? Because they're all going to run like madmen to that pie and they're going to try to eat. And some people will eat 2 pieces, some people will eat half a piece. And then a lot of, like I said, the people that don't go to the gym, they will never eat a pie because they are still running to the pie. You know what I mean? So how can we fix that? We could adding some rules, some synchronization technique. And that's where the yellow flag comes in, right? So we could say everybody, 10 people there, everybody can eat from the pie, but you first need to take the flag. If you have the flag, you can eat your piece of pie. If you're done, you need to give your flag to the next in the line. And only the person with the flag can eat from the pie. So what's going to happen is that all these 10 people, they're going to go one by one with the flag. They're going to eat the pie. They're going to give the flag to the next one. And so everybody is synchronized. Everybody will have its piece of the pie. Right? Cool. So how do we do that? We do that with the sync mutex, right? So how we're going to save this is basically we need to open up our main here. And we have a state. And we are going to say, we're going to add a sync mutex, right? To be honest, we're going to add a sync RW mutex. You could use basically one of both. It doesn't really matter. But most of the time, I'm using RW mutex. That's basically a read-write mutex. With this mutex, you can basically read. You could separate your reads and your writes with different things. But that doesn't really matter. Everything will be clear. Use RW mutex. Use just mutex. Actually, to be honest, let's just use a mutex. It doesn't really matter, right? We're going to probably see that RW mutex in some further episodes. We're going to just use a mutex, right? Nothing we need to do with this mutex. The only thing we need to do basically is we can delete, close this file by the way. We're going to say we're going to do something else. We're going to open up main real quick. We're going to make it a little bit cleaner, right? So we do, in this case, what we do is basically we say state count, and then we directly assign it to that variable. But we are going to make a function actually, and we're going to say func as, oh yeah, let's make it a pointer then. It doesn't really matter. As state, and we're gonna say set state, and that's going to be an integer, y integer, right? And what it's gonna do is basically simple, as count equals y. That's the only thing it's gonna do, right? I'm first going to it in a bad way, so you see that the refactoring of this little program is the same output as we had before. The only thing we need to do here is make this state a pointer, just like that, and I'm adding pointers here and there just so you guys get familiar with them, right? And instead of saying state count equals 1, but we don't need this main function anymore, by the way, we're going to open up our test, and we're going to say, instead of state count equals y plus 1, we're going to say state set state I plus 1, delete everything, call of entity copies value of lock, yada yada. That's true because we need this reference here to the state. And now what we're going to do is we're going to run this again with the race flag, and we still have this race condition, but we have a little refactor, right? So, and you will see why I did this refactor. So now we're going to open up main again, where our code, where our state lives. And we're going to say, we're going to protect our count value just like a flag, right? We're going to implement the flag logic, the yellow flag logic inside of our state. So the first thing we're going to do is we're going to say s dot, to be honest, let's say mu from Mutex, always a good idiom to name your mutexes mu from Mutex. Everybody that will see that will know, oh, that's a mutex, right? So we're going to say smu, we're going to lock it here, right? And then we could do this, for example, smu.unlock. It's very important that you always unlock your mutex, because if you don't lock your mutex, it's basically, if you say lock, that basically means, hey, here is the yellow flag. But if you don't say unlock, that guy will keep having the yellow flag in his hand, so everybody is waiting, is not eating pie, you know what I mean? So you need to say unlock, that basically means give the flag to the next one, right? Free up the mutex for the next in the line. That's what it means. You could do it like this, right? But you could also do it like this and say defer, right? And defer will basically, everything after defer, this line here, will execute just before the function returns. That's the only thing that defer does. It's very convenient because sometimes you're returning here and you still want to defer, you can, right? In our case, we could basically do this, right? And paste it in here. Doesn't really matter. Up to you. I prefer defer and paste it here, right? So we have this mutex logic nice and tight together, right? Okay, cool. So now we have our flag logic, and let's do the race thingy here. Boom. And now we have no race conditions anymore, right? Pretty fine. Of course, the count is this weird thingy, but it doesn't really matter, right? You don't need to worry about that stuff. Yeah, that's what basically mutexes. Very important. Very, very important. If we don't unlock this mutex, what's going to happen is this. Just like that, and it's basically going to keep hanging, right? You see, the program is not exiting because they are waiting for the flag to be passed, and it's never happening, right? So let's put that back in. This is basically mutexes. Very simple, but very important to do, right? Each time you're going to make a map or something that we need to use concurrently, because maps are not concurrent safe, we are going to implement the mutex for that map for sure. All right, so now we're going to basically discuss atomic values. Atomic values is basically a way to increment, decrement, add stuff atomically in an atomic way. And an atomic way basically means that you are also synchronized just like a mutex. Although I'm only using atomic values for example, counters or booleans or this small stuff. I never use atomic value because you can also overuse atomic values. I'm only using atomic values for small stuff. And how does that work? Well, it's very simple. Let's delete the sync mutex here, right? We're going to delete this mutex, and then we're going to basically run our test once again. And you can see we still we have our race condition back in the game. Bad news, bad news. What we're going to do instead of this count, we're going to make it an int32, I think. And then we are going to say each time we're going to set a state, we are going to say atomic at int32. And we're going to pass in the reference of count, right? And y, right? Wait, it's going to be scount, by the way. I cannot use int, that's true. So we need to convert this into an int32. Just like that, right? That's what we're going to do. And that should be race free. It's race free, like you see. Let me run it again, clear the screen, run it again. Boom. It's, again, race free. Because why? Because we're basically adding the new state to the count atomically. That's the only thing you need to know. How much are you going to encounter atomic values? Less. You probably are going to use mutexes much more. Atomic values, maybe. But you just need to know, because not everybody knows this. Very important. Know it in the back of your head that there is also something like atomic values you can use for simple stuff like an order count, counting, booleans, maybe, yeah, small numbers, all that stuff, small data sets. That's what I'm doing. And if you wanna, you could do a lot of stuff with atomics, right? Like I said, just look up, if you look up the standard library, you can see add int32. We can also have something like load. That's basically loading the value back from memory. It's very important because if you want to access the state, you really want to do something with the state, you want to read the state, you need to load it first, right? That's basically atomic values. I think that's it. Like I said, we can go much more into detail and much more into depth, but it's already complicated enough and I don't like that. You just need to know the basics for now, because things will get complexer over time and over time and over time. And if we add complexity right now from the beginning, like I said, your reward levels will be completely depleted. Dopamine levels has left the chat. We don't want that. We want to stay sharp. We want to stay at the sea level. That's important. We want to stay at the sea level, but knowing what's on the horizon vaguely. So we know which direction we need to go when we need it. That's programming. That's learning, right? Don't try to paint the whole canvas. Don't try to see the whole horizon in detail, because you don't know where to look. You're going to be imponated, right? You're going to be insecure. If you just see the horizon vaguely and you know, okay, that's north, there's a mountain, there's, I don't know, a ship, there's a treasure chest, I think, then if you need the treasure chest, you can go into that direction. If you want to learn more about the mountains, you can go into the direction of the mountains if you need it. That's important. All right. I'll see you in the next video. Peace.